So the question here was, if we define an equivalence relation, actually I suppose it should just be a relation, on the set of all people, okay, by x is related to y if and only if x and y are siblings. Okay, and siblings here can include, well, there was some argument on Slack about what siblings include the other day, so I don't know, let's say if they would each consider one another to be a sibling in the family. We're not going to police biology. So which of these three properties that an equivalence relation must satisfy all three of, which of them are satisfied by this relation? There was considerable agreement that the symmetric property was satisfied by the sibling relation. Now, why is that? Why did people say that this relation satisfies the symmetric property? What is the symmetric property? Fine.
So it says if one person is another person's brother, that second person is that other person's sibling.
Okay.
We're switching basically the order of the two being each other's siblings around.
Sure, you're just switching the order around. So if y is sibling, then y is x's sibling. I guess this is why I was careful to say we can define this by the two of these people agreeing that they are siblings of one another. Yeah, because it is symmetric, right? If I'm your biological brother, then you are my biological sibling, at least, right? So yeah, the symmetric property I think we can make a pretty straightforward argument for. What about the other properties? So tell me about the reflexive property. Not many people said that this was satisfied by the sibling relation. Why not? If it's not satisfied, what kind of a counterexample can you come up with? First of all, how would the reflexive property read in the case of this relation?
X is X's sibling.
X is X's sibling.
You are your own sibling.
Are you your own sibling? We all contain multitudes, do we not?
Definition, if we agree.
If I agree with myself that I am my own brother or sister, perhaps. But yeah, no, I think usually in the traditional understanding of what sibling means, probably we would argue that this is not. And that creates other problems on this list also. So why were people pessimistic about the transitive property? How would the transitive property read in this example? Yeah.
If x is y's sibling.
If x is y's sibling.
And y is z's sibling.
Okay.
Then x is z's sibling.
Yeah. Then. So what's the reason for the pessimism here? Why might this not be the case? Yeah.
Brian and I had a conversation on Slack about like if it was half siblings or
Oh, okay.
have the same parents. Because originally I thought it was strictly biological, so I did put symmetric and transitive.
Okay. But if you have different set of parents, so maybe you and I would say that we're siblings, and then you and somebody else would say that you're siblings, but if there's a different set of parents in the mix, then maybe I'm not as close to that third person as I am to the person I'm connected to them through. So yeah, maybe not. Again, a lot of this depends on definitions, as it always does in mathematics. And we hope to think elsewhere in the logical world as well. So there's room for some disagreement about definitions, but the important part for me, and I hope for all of us, is that it got us thinking again about what equivalence relations are. What are these properties that we want equivalence relations to satisfy? Because the fact is, if we do have an equivalence relation, and this is the big idea of the day today, that equivalence relations also do something very powerful. And this is the purpose of the last question on here that's going to get us into today. Equivalence relations do an important thing. They partition sets into equivalence classes. So here's an example. There's an exercise in the online textbook that I didn't assign as part of the homework, I don't think, but I want to kind of talk about it a little bit right now. So here's a equivalence relation. Why it's an equivalence relation is a question we'll maybe defer to another time. But it's an equivalence relation on the xy plane. So the set here is the set R2. And the definition of this equivalence relation is that 2 points, x1, y1, is related to a second point, x2, y2. if and only if, the sum of the squares, x1 squared plus y1 squared, and x2 squared plus y2 squared, are equal. So there's a definition of a relation on the points in the xy plane. It's not too terribly challenging, I think, to convince ourselves that this satisfies all three properties, that every point is going to be related to itself, that if one point is related to another, then that other is related to the first. That's going to follow from the symmetry of the equal sign, right? Equal sign works both ways. And same thing with transitive property, also satisfied because of the transitive property of equality, right? So these are all satisfied. But my question is, how does this equivalence relation partition the xy plane? What do the equivalence classes of this look like? So remind me, what do we mean by equivalence class? Let's suppose I have a point on the xy plane, 3, 4. Right? My question is, what is the equivalence class of that point? Equivalence class of the point 3, 4. First of all, what do we mean by equivalence class? Right?
So equivalence class is the set of the elements in the bigger set,
Okay.
or the universal set or whatever you're working with, that satisfy that it shares the equivalence relation with that point. So in
Yeah.
this case, 3, 4 is going to be whatever it shares with. Yeah.
Right. So when we say equivalence class, and we usually use some brackets to denote this, so brackets around 3, 4 means the equivalence class of 3, 4. It's the set of all points in my larger set which are related via this relation to the point 3, 4. So all of 3, 4's relatives. Well, how would I know what's related to 3, 4 by this equivalence relation? So if I just plunk this definition of my equivalence relation into the observation here that defines membership in that equivalence class, then what do I get here? Let me use a different color because it's getting hard to read. X squared plus y squared must be equal to what? 3 squared plus 4 squared. Yeah. So this equation here defines membership in this equivalence class. It's going to consist of all the points x, y, for which x squared plus y squared is equal to 3 squared plus 4 squared. 3 squared plus 4 squared is 25. So it turns out this equivalence class is, what does it look like if we were to visualize it in the xy plane?
Circle radius 5.
It's a circle, radius 5, centered at 0, 0. Here is the equivalence class of the point 3, 4. Obviously, the point belongs to its own equivalence class because it's a reflexive relation. And any 2 points that lie on this red circle share the same equivalence class because of that symmetric property. If one of them is there and the other one is there, then it goes the other way also. Same thing with transitivity. So, all right, but this is one equivalence class. Right? It's the equivalence class that contains the point 3, 4. What do all of the equivalence classes look like for this equivalence relation? Colleen? Well, we hope so, because one of the things that is necessary in order to make a partition is that partition means what? First of all, it means that all elements of our larger set, in this example it's R2, all elements belong to how many equivalence classes? More than one ever? Less than one ever?
Just one.
One and only one belong to exactly one equivalence class. And so what that means is that if I take all the equivalence classes and I union them together, then as Colleen says, we should get the whole set R2 back, right? So these equivalence classes need to cover all of R2 and cover it in such a way that none of them are overlapping one another, right? Because each element of R2 belongs to one and only one equivalence class. Okay, and the equivalence class of the point 3, 4 is this circle. What do the equivalence classes of other points look like for this equivalence relation? Like instead of 3, 4, what if I chose 1, 1 or something?
A circle of another radius.
A circle of a different radius. So let me get my Desmos foo. So the point 2, 2, for example, this is its equivalence class. The point we started with, 3, 4, that was its equivalence class. But you'll notice all of the equivalence classes of this equivalence relation are circles. Right? And all of the circles have the same center. They have different radii. But since they all have the same center, how many times can two different circles intersect in this family? Two different circles will never intersect. And so the way that this equivalence relation partitions the plane is it partitions it into a bunch of concentric circles. Right? And each circle is just the equivalence class, well, of all of its points, of course, that are on it. So that makes a nice partition. In fact, it's a nice enough partition that in geometry we would actually call it a foliation. It varies. Each of the curves that make up this partition are nice and smooth, and also the way that they vary from one equivalence class to another is also nice and smooth. So it kind of gives this nice polar coordinate way of kind of visualizing what how this plane is being carved up by this equivalence relation. And so then I guess the last thing I wanted to ask is if I wanted to write down the set of all equivalence classes. All equivalence classes. Hopefully we're persuaded that this is the set of all circles centered at the origin. How big is this set? Kind of a vague question.
10.
Infinite set? 10? Well, 10.
10 big.
10 big. It's big. Well, but how big is big? Like, how would we understand how many elements there are in this set of all equivalence classes? Maybe another way to ask this question is, in order to single out one of these equivalence classes, what kind of information do you have to give me? What separates these different circles one from another? Maybe the radius, right? If you give me a radius, I can show you on here the equivalence class that's made up of the circle that has that radius, right? But how many different radii could we choose?
Just between 1 and 2, you could have infinite.
That's right. We have as many possible radii to choose from as we have non-negative real numbers, which is an awful lot of numbers, right? But somehow, I guess my question is, this looks like, I'm going to be vague for today, it looks like, let's say, R plus, right? The set, or maybe I'll say R greater than or equal to 0. Right, the set of all non-negative real numbers. If you give me a non-negative real number, I give you an equivalence class. And if two of you give me different non-negative real numbers, I give you different equivalence classes. Right? So there is a one-to-one and onto correspondence between the non-negative real numbers that you can give me and the circle that I can show you that's a part of this family of equivalence classes. Right? And so
the R greater than or less.
So when I say R greater than or equal to 0, I mean it's the set of all real numbers which are greater than or equal to 0.
Okay.
R is greater
Why
than or
does
equal
it matter that it's greater than 0? If I gave you -3 and -4, you'd have the same one. You're squaring two numbers.
But then you wouldn't be giving me a radius,
You're
right?
right.
So Alexis' idea is give us a radius, and then I'll give you the circle. But we could have done it the other way also, right? But actually I want to pause on that for a second. So if we did it the other way, if instead of giving me a radius, you give me a point, then it's always true that I will know how to give you the equivalence class of that point. But it's not going to be true that if two of you give me different points, I'm going to give you different circles. Why?
Some points can end up on the same circle.
That's right. So -3, -4, and +3, +4, different points, they end up on the same circle. So that correspondence would no longer be one-to-one, because different points could give me different circles. But the correspondence of radius to circle is one-to-one. And it also happens to be onto if we allow the radii to range from 0 out to infinity. And therefore, this set of equivalence classes partitions the xy plane, but it does so in such a way that my equivalence classes at the end of the day are indexed by the positive real numbers. So we started out with the xy plane in two-dimensional space, and then when we carved it up into these equivalence classes, that set of equivalence classes is smaller somehow. It's lower dimension, right? It's just a single real number that's needed to tell me what the equivalence classes are, as opposed to two real numbers which would be needed to tell me the whole xy plane.